Students, this is the last section of 5-6, and we are going to talk about inverse relations and inverse functions. By the end of this section, you will be able to represent the inverse of a relation and using a table, a graph, or an equation. You should be able to write an equation for the inverse of a function by restricting its domain. And the last thing, you should be able to verify that one function is the inverse of another function, and we're going to use our composition rules to do that. So think about this as we're going through this. How can we find the inverse of function and verify that the two functions are inverses? That's our goal. And you remember what a function is. It's a relation in which each element of the domain and that would be your x's, and that would be your x values, corresponds to exactly one element in the range. And we've talked about this since Algebra 1. Exactly one element in the range. And that would be your y values. And hopefully you remember the vertical line test. That is one way we can test to see if it doesn't pass the vertical line test, then it's not a function. It can be in a relation, but it's not a function. So the inverse relation, and we're going to go through some examples of these in a little bit, is formed when the roles of the independent and dependent and dependent variables are reversed. In other words, the x becomes the y's and the y's become the x. So the x's from your first function become the y's from the second function, and the y's of the first function become the x's of the second function. And that's just my shorthand. I just made that up. So nothing official about that, but that's one way to think about it. Now, if it's an inverse function, it is an inverse relation like we talked about here. And then that is also a function. So we're putting these first two vocabulary words together. So the way we denote it, we do f to the -1 of x. That's my inverse function. This is the inverse function of f of x. So anytime you see the -1, that's talking about the inverse function. Let's go right to a table and look at the table and see if we can see the inverse relation. So first we're just going to talk about the relation and not whether it's a function or not. We'll determine that later. So if this is x and this is y, the inverse would be the new x and the new y would be flip-flopped around. I was trying to think if there's an easy way to do this, but anyway. So the y becomes the x, so we do 1, 4, 3, 1, and the x becomes the y, and you keep them lined up. All right, so that's all we do is flip-flop. So the y becomes the x, and the x becomes the y for the inverse. Now it says, is the relation a function? Well, remember, you have to have exactly one output for every input. Well, look at here. I have two inputs of 1, and that means in this case, I have two different outputs. So if I were to graph just those points, I'd have 1, -2, and 1, 1, and they would not pass the vertical line test, right? So I can't have two different x's here with two different y. The same x with two different y's. I cannot have that. So no, it is not a function. Oh, sorry. Is the inverse? No, this is not. Now look at, I'm sorry, I didn't look at this one has unique x's, so yes, this one, the first one is a function. And could you graph the tables? Sure, you could graph them. I didn't do all of the points here, I just did, but 4, -1 would look like this, and 3, 0 would look like that. And so it's just, but you can see from the one I did that vertical line test does not work. So if an inverse relation of a function f is itself a function, so if this were a function, it's called the inverse function of f, and it's written like this. So this one is not. We're going to get into some that are. I want you to try it. Write the table of the inverse relation and then determine whether it's a function or not. So I can see that I have unique x's, and that's all I need to know. If the x's are all unique, it doesn't matter what the y's are. So it is a function. And you could graph those points and see it too. It'd be a little random. I don't think this actually is a algebraic function. Here's another one to try. Just look at the relationship here, and maybe you don't even need to make a table. Maybe you can do that in your head and determine. But try it and I'll be right back. You may have noticed that you have two x's that are the same, but these are different. And again, that would mean it's not a function. The inverse is not a function. This one also, if you look at, this is interesting too, because if you looked at the first relation, I have two different x's here with two different y's. So that's not a function either. So neither one is a function on that. Now what if I have an equation? How would I do this? How can I represent the inverse relation of f algebraically? Because we can't be making tables for every single thing, right? That would be a lot of work. So we have our rules here, and you'll want to write these rules down, and then we'll do some examples so you'll be able to do this on your own. So first I'll show you how to do it. You set f of x to y. So instead of f of x equals x squared, I would just say y equals x squared. So that's my first step. And then switch the roles of x and y. Remember, that's what we talked about. So instead of a y, that would be an x. Instead of an x, that would be a y. Well, that's a legitimate equation, but we want it for terms of y equals. Remember, we could raise this to the inverse, or excuse me, the reciprocal power, which is 1/2. So if I do it over there, I have to do it over here. Now, technically, this is plus or minus the x. All right, so that is my inverse relation. We're going to start with that. Now the next one, I went ahead and graphed it. So f of x is x squared. So that's this one right here. That's the blue one. Now the y equals plus or minus square root of x. That's actually the red here and the red here. One's the plus and one's the minus. And you could look at it and you could, right off the bat, you could see that I have two values of y for the same value of x. So it's not a function. I know that that is not a function, but it is a relation. It's a valid relation. Now notice the domain here. The range here is y is greater than 0. So the range, because this is as low as y can go, and what happens is the range of the first one becomes the domain of the inverse. So on this one, x has to be greater than or equal to 0. That's kind of a fun little fact. We're going to switch the domain and range of a relation and its inverse. They just flip-flop around. And that makes sense. And another unique thing about this is I could draw the line y equals x. That's this line right here. And I could actually reflect the blue one over this line, and I could fold the paper in half right there, and it would line up to this red one. This is always true for every inverse. So the inverse of any function f, or any relation f, is the reflection of the graph on in this case, y equals x squared, across y equals x or x equals y. This is always true. You can reflect it. Fold it in half and they'd match up. I want you to try this one using those steps. Do you remember the first step? Was f of x, set f of x to y, and then, let's look back here how I worded it. Set f of x to y, switch the roles of x and y. Switch the roles of x and y, and then you would solve for y. So yeah, you're putting it in y equals format. Solve for y. So go ahead and try that and see what you come up with. This right here, y equals x minus 1 over 2. Now, I could still graph that, but I'm going to simplify this out here a little bit. That's the same thing as 1/2 x, right, minus 1/2. So this is going to help me graph it a little bit. The first one, the y-intercept is 1 and a slope is 2. So it would look something like this. All right. The second one, let me see if I can get a different color here. The second one, this one, the y-intercept would be 1/2, which would be about right here, and I go down 1 over 2. Oops. Oh, excuse me, up 1 over 2. Up 1 over 2 would be about right here. This is a little tricky to do. I should have just graphed it probably. Oh, I think my hands are doing that. Up 1 over 2. So it's like a slider slope right there. There we go. Now I could, x equals y would be like a line right here, and it would go right through that. It's not very straight, but this would be a reflection over that. And you could do a better job doing them both on Desmos, and you could figure it out too. Now it says, how can you use the graph to determine if the inverse of f is a function? Well, the graph will tell you that for every x value, I only have one y value, right? Only one unique. There's no doubling over there, so it would pass the vertical line test. And if you think about it, are all lines functions? Well, they are, as long as we're not doing any restrictions on them. Sure. Now the question is, all inverse relations of lines functions? Well, they must be in this situation. Sometimes we do have to restrict the domain so that we can produce an inverse function. Remember when we did the y equals x squared, you'd get 0, 0, 1, 1, 2, 4, negative 2. So you get something like this, a nice little parabola. And that is a function, but remember what happened when I inversed it? I got y equals plus or minus the square root of x. Remember when we did that? So let's go ahead and let's do that one. And I ended up, it goes this way, and then 4 becomes 2. So it kind of goes like this, and then does the same thing down here. But remember that this is not a function as it's written because of this problem right here, right? But if I restrict the domain or the range, maybe I have to restrict the range too. If I make some kind of restriction, so this is a function, but if I want to restrict this one right here, I would have to restrict y would have to be positive, right? Greater than or equal to 0. So the range of this one is restricted, so I would have to restrict the domain of the first function. So this is the domain would have to be x greater than or equal to 0. In other words, I'd have to get rid of this piece right here. And then I could draw my line. That would get rid of that one, and that would reflect that over that line. I put some graphs on here. Obviously, you can't. Well, if you printed out your notes, you can, but otherwise you have to get some graph paper to graph it yourself. But again, you can use some Desmos if you want. This one, the first one, though, is a little tricky to do the inverse. I'll get you started. Because if you did y equals x squared plus 8x plus 16, and then you flipped it around, you'd end up with this thing. Well, that's a little messy to try to find what that would look like. So what I'm going to recommend is for f of x, you do a table. And I'm going to give you some values here to make it a little easier. Let's do -4, 2, 0, -6, and -8. Try those and see what you come up with. And then for your inverse, you would just flip-flop the x and y's around. So over here you'd have -4, -2, 0, -6, 8, -8. And then this one can be done algebraically a little easier. And we'll try both of those and see what happens when you get back. Okay. Now notice I graphed it over here, and then what I did was I graphed these points over here. So it is a square root of some sort, and it was pretty easy just to graph. Now I know that in order to be a function, this can't exist, right? So I have to limit x being greater than a -4. And you might remember that this is, the x is the opposite, this is the vertex, opposite of b over 2a, right? That can give you that point right there. And that would be opposite of b would -8 over 2 would give me the -4. So that would give me this point right here because that's where x is at. So this would give me the y. Remember, we just interchange the domain and the range when we do inverses. So the same thing with the restriction. So on this one, I would have to restrict the x being greater, so I'd have to get rid of this part in order to have an actual function for this one. So that takes a look at your domain here, becomes your range restriction here. And notice when you take the square root, you're actually, technically you're doing plus or minus, but to make it restricted, you would just do y equals square root of x plus 9. That would be your restriction on that one. All right. Now we're going to find an equation of an inverse function. And we're going to do this like we did before. We could graph. This is a rational function here. We could graph that one, right? This is the positive of x minus 2. We know that it would be shifted to, let's see, minus 2 shifts it to the right 2, right? And if I put 2 in there, I get 0 out. So I'm shifting everything to the right. This is for the f of x. And then you could just put some numbers in there. Like I could put 6 in there, and then 6 minus 2 is 4, and square root of 4 is 2. So I know it would go something like this. So the domain of the f of x is x has to be greater than or equal to 2. So this is as small as it can get. Now the range would be y greater than or equal to 0. So that's the smallest, that point right there. Remember the 2, 0. Now, find algebraically the inverse. So I go through my steps. And then I flip-flop the x and the y. Now here I'm going to square both sides. Square both sides. So I get x squared equals y minus 2. So I'd have to add 2 to both sides. X squared plus 2 equals y. Now you remember that that would be right here. So when x is 0, so I'm taking the x squared function and just pushing it up 2. 2 would be 4, and then 3 would be way up there, right? Yeah, right there. Okay, whoops. All right. Now, because I restricted the x here, I would restrict the y here, and vice versa. So I have 2 restrictions here, and so I would have the restrictions there. So I wouldn't, let me show you that. So on the inverse of x, my y would be greater than or equal to 2, and my x would be greater than or equal to 0. And that's obvious from the graph. So if I graph them and then I take a little line like this, where x equals y or y equals x, it should be, one should be the reflection of the other one. Let's see, I think we're going to, yeah, we're going to just stop right here, and then we'll use this one next time for a warm-up, and that should get you everything you need to be able to do 5, 6, day 1, Math Excel, and after that, you'll be done for the day and today's lesson.